Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members to our discussion for today, and I kindly request for those who have not subscribed to subscribe, engage us in the comment section and also ring that notification bell to be getting updates on our various uploads in mathematics and sciences. I'd also like to encourage our members to be checking our description boxes. I'm going to put a link of other videos. There are going to be videos under a similar discussion, and of course we are going to be having a range of other videos from various topics that we are going to do, of course, particularly for this one on electricity and magnetism. Now in this particular discussion, I'm going to look at the magnetic field inside a current carrying conductor, and this is going to be following the previous discussions we have had extensively on a number of topics. And this, of course, includes the electric charge, the concept of magnetic and electric fields, and other related content. Now, in this particular case, I'd like to remind ourselves of the previous discussion we had on the concept of Ampere's law. And this is going to assist us in trying to interpret basically how we can find the magnetic field inside a current carrying conductor. Now, in this case, I'm going to have these particular conductors, which are basically 1 and 2. And these are going to, of course, carry current through this specific area which I'm going to demarcate, basically which is going to be a closed path. Now, in this case, this closed path is going to enclose an area which is going to be assisting us trying to define this specific aspect of the Ampere's law as we had discussed from our previous topic. Now, in this case, we had considered this specific part, and of course, we said that if this closed path is going to have a current around it, and we are going to imagine that this part is made up of short segments. Now, in this case, we had given this specific, suppose the length of this particular part, the entire length of this particular part is given as L, then we can have a small segment of this specific length given in terms of a delta L given as such, or in some cases we're going to have it given as a DL. So let's just give it as a DL given as such. So suppose we have a small segment of this particular length of this closed path that is enclosing two current carrying conductors given in terms of a DL. We can see that from experimental data, if we take the product of the length of each segment which are making up the length of this particular path, and the influence which is going to be, of course, the magnetic field being created by this specific segment. Remember, this is a current carrying conductor, and from some of the discussion we have had from our previous discussion, we said that there's going to be magnetic fields which are going to be created in this particular case. And those gave us some aspects like the right hand grip rule, which we use to define the direction of that specific magnetic field. Now, in this particular case, we can have a specific law, which basically is going to be taking the product of each of this length and the component of magnetic field, which is going to be parallel to this specific length. Now, if we take the product of this specific magnetic field and the component of this specific length and try to sum up all the entire components which are found in this particular case with the respective parallel magnetic field component, the result is going to be equivalent to the product of a mu naught given as such. And of course, we're going to see that that product is as well going to be the product of mu naught and the current which is enclosed in this specific path. Now, in this case, this gave us the concept of Ampere's law, which we gave particularly in terms of a mathematical representation, which I'm going to give in terms of particularly this specific representation in a summary form. Now, the product of this magnetic field elements and the length segment is going to give us mu naught and the current which is enclosed. And this, of course, summed up what we referred to as Ampere's law. Now, in considering the various effects which we are going to realize in the, of course, this specific conductor, now I'm going to give this one for figure A and B, whereby we're going to consider for figure A in trying to see what is the magnitude of the magnetic field that is going to be, of course, found inside a current carrying conductor using this specific concept of Ampere's law. Now, in this case, I'm going to be, of course, emphasizing on this specific law. Now, from other discussions which we had discussed, of course, we had considered a circular curve. or in other words, a circular path, which we refer to as the Unveiling curve. And this Unveiling curve, of course, was in form of this specific curve, which we are going to give this specific point. Now, I'm going to name this one as an Unveiling curve, and that is going to assist us in trying to interpret this specific information. Now, henceforth, we are going to consider the Ampere's law, considering this specific Unveiling curve, whereby we're going to see that if this is going to be the summation of those length segments which we are going to give in terms of a dl, then considering the Unveiling curve of a radius r, then therefore this is going to be forming a circumference of this inner circle which I've given in terms of a dotted lines. Now from our geometry, then therefore that's going to imply that we're going to use the circumference of this specific area in trying to define this specific aspect of Ampere's law. And that's going to assist us in trying to find this specific aspect of what we refer to as the magnetic field. Now in this case, I'm going to look at this specific curve and we're going to do an analysis. And now that we have defined Ampere's law from our last discussion, then therefore it's going to be easier for us to analyze that specific diagram. Now we're going to look at this one, and from our previous discussion we said that the magnetic field basically is going to be tangential to the Unveiling curve, and in this case then therefore we are going to consider the Unveiling curve of this specific radius or this specific radii. I've considered this Unveiling curve and the outer circle which has got a radius of r. Therefore we're going to consider that Unveiling curve of radius r. So this is going to have a magnetic field given as this is going to be the magnetic field, and of course we are going to have our Unveiling curve of radius or of radii. We're going to have of radius, of course, r, which is smaller than the greater radius of r, which is going to be a radius of the conductor given as such. And from this one, we can define Ampere's law by use of this specific information, whereby we have said that the closed path integral for this specific definition, which we have given for Ampere's law, can be given in terms of the magnetic field and this one. And this is going to give us the product of mu naught and the current enclosed, as we said. Now, in trying to find the integral for this, we're going to have the magnetic field taken out since it's going to be a constant, and therefore we're going to find the summation of these specific elements of dl, which basically are going to be equivalent to the current enclosed times mu naught, which is a permittivity of free space. And therefore we're going to see that the current enclosed in this particular case is going to be directly proportional to the cross-sectional. So we are going to have this one as directly proportional to the cross-sectional. So this is a cross-sectional area. So kindly take note of this specific initials which I'm giving for the sake of our space. So the current enclosed is directly proportional to the cross-sectional area in this specific case. And therefore we can have a relationship between the magnetic field which is going to be created in this particular case, and try to see what are some of the relationship we are going to achieve. Now we are going to see that from experimental values which have been obtained, there is a relationship between the magnetic field and the radius which we have seen, or the radii which we are going to use for R1 or the small r, and the capital or the capital R which we are going to use in this particular case. And we can indicate that one whereby we're going to see that the magnetic field is going to be directly proportional to the cross-sectional area. Now this is going to be a curve which is going to have a positive increase from this particular point of origin. Now whereby we are going to have the magnetic field directly proportional to the cross-sectional area of this specific, of course, what we refer to as the small radius given as such. But now this is going to be the case for current inside this specific conductor. But on the other side, or on the flip side, we're going to see that specific curve that is going to be declining, going in a curve. So this is going to be somehow linear, as we can see, but that one is going to be having a specific variation. Now this is going to be the magnetic field given that specific inverse proportionality with that particular area at that particular point. Now we can see at this specific point whereby we have R, it's going to peak. The magnetic field is going to be maximum at this particular point, and therefore this is going to be the case outside this specific conductor. Now, from a small analysis of this curve, of course, we're going to use that specific information to assist us in trying to interpret that one, basically what it means. Now, we can have a relationship then, therefore, between this specific current. Now that we have defined the relationship between the magnetic field and the current, we can have a relationship between this current, which is enclosed, and of course, the area of the two circles, which are defined by radii r and small r and capital R, whereby we're going to have the current enclosed all over the current, which is going to be indicated given as I, is equivalent to the ratio between the areas of the small radius and the area of the big radius, if I may refer to them as that. And from this one, we can find the aspect of the current which is enclosed, of course, which we are going to be after in this specific discussion. Therefore, we can have the current enclosed as a subject of this specific formula, equivalent to the current times pi r squared, the small r over pi capital R, given as such. So we can just do a simplification of this specific relationship and therefore find the current enclosed is equivalent to current times, of course, that specific ratio given as such. And this basically is going to define the relationship between this specific radii, which we are going to see, and the relationship with the current which is enclosed. Now, using Ampere's law, we can be able to evaluate this specific relationship, which is going to assist us in trying to find this specific aspect of the magnetic field. So kindly take note of this particular relationship which we have given at the lower part of the board. And therefore, I'm going to proceed in trying to find how we can define the magnetic field using our previous discussion from the Ampere's law, having discussed on the ratios of this specific radii and the current inside that specific, or the current enclosed in that specific case. So from Ampere's law, we had said that this is going to be given in terms of this specific representation, whereby the current enclosed, the product of the current enclosed and mu, which is mu naught, permittivity of free space, is equivalent to the summation of the length element and the magnetic field in this particular case. So we have to consider this one for a closed interval, closed path, which is of course going to be our circumference, and therefore we can evaluate this one and find that we are going to take out the magnetic field. And for this specific aspect of the length element, then therefore this is going to give us current. This is going to be mu naught. But remember, from this one, we have defined a current enclosed as the ratio between this specific radii. So therefore, we are going to do a direct substitution for this one in order for us to find the representation for this given in terms of R given as such. So this is going to form our definition for that. But we have said that from our illustration above, this dl, the summation of this, all these elements of dl are going to form what we refer to as, of course, the circumference. And we can find the circumference of this small, of course, or rather this Amperian curve using this specific 2 pi r given as such. So this is going to result in the relationship which is going to be given as such. And of course, we're going to see that this eventually is going to lead to a formula representing the magnetic field inside this specific conductor given in terms of R all over 2 pi r given as such. And this is going to give us the magnetic field inside a current carrying conductor given using this specific formula. So kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section, and also ring that notification bell to be getting various updates on topics in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.